Hello everyone. In today's session of CCNA series, I will discuss traffic policing and shaping. QoS allows two tools for managing traffic that exceeds a specific rate. Okay, these two tools are traffic shaping and traffic policing. Both policing and shaping monitor the bit rate of the packets that flow through the device and enforce rate limiting, where excess IP traffic is either dropped, marked, or delayed. So basically, policers discard and or remark packet, whereas shaper hold packets in queues to delay the packets. So policers discards or remark the packet. Shapers hold packets in queue to delay the packet. These tools are most often used at the WAN edge in an enterprise network design. Let's go ahead and discuss about these tools, starting with an analogy of policing. So, an analogy for traffic policing in quality of service could be comparing it to a traffic police officer on a busy road. Just as a traffic police officer monitors and controls the flow of vehicles to ensure smooth traffic movement, traffic policing in QoS involves monitoring and controlling the flow of network traffic to ensure that it adheres to predefined rules or limits. For example, imagine a road where the speed limit is 45 miles per hour. If a vehicle is speeding and exceeds the limit, the traffic police officer can stop the vehicle or impose a penalty to enforce compliance with the speed limit. Similarly, in an IP network, traffic policing involves monitoring the rate of incoming traffic and dropping or marking packet that exceeds a specified rate or violates certain rules, such as ensuring that certain type of traffic adhere to agreed upon uh, bandwidth limits or priorities. Actually, in both cases, the goal is to ensure that traffic flows smoothly and efficiently without one type of traffic dominating or causing congestion that affects other types of traffic. So let's see what policing is. Policing allows you to control the maximum rate of traffic that is transmitted or received on an interface. So policing is usually implemented on the provider side and will either drop or remark traffic that exceeds the provided committed rate, also known as CIR, or you can say committed information rate. Traffic that falls within the CIR is transmitted, whereas traffic that exceeds the CIR is dropped or remarked and transmitted with different priority. Actually, traffic arrives at networking devices at varying rate with valleys and spikes. The policer would measure that rate and take required action. The horizontal dashed line represents the policing rate. When you apply policing, the policers discard any packet that violates the configured policing rate. And if you compare this, the traffic flow graph after applying policing, the policer chops off the top of the graph at the policing rate. Okay, if you see the graph above the policing rate is chopped off. So policer also allows a burst of traffic only beyond the policing rate only for a short period of time after a period of low activity. So let's look where to use this policing. For example, let's say you have a small office network and have 1 Gbps internet connection with your ISP. To ensure you cannot exceed that rate, your ISP configures a policer on the ingress interface of the device, limiting your bandwidth to 1 Gbps. The first packet entering the ISP device is within 1 Gbps rate. Second is also below 1 Gbps as well, but the third packet is above the rate, that is 2 Gbps. The policer accepts the first and second packet and can either drop the third packet or remark it. and then send it to further QoS processing. So customers receive what they are paid for. So policer can discard excess traffic, but they can also remark it. Let's move on to another tool, that is shaping. Let me explain you this with an analogy again. So QoS traffic shaping can be explained using an analogy of a water tank with a faucet. Imagine you have a water tank that can only release a certain amount of water per second. If you open the faucet too wide, the water flows out quickly, possibly causing spills or water pressures. Now, think of QoS traffic shaping as adjusting the faucet to control the flow of water. Instead of water, you can think of a packets. If you turn on the faucet to a specific setting, it limits the flow of water to a steady, manageable rate, preventing the spills and pressure problems. So, similarly, in networking, QoS traffic shaping works similarly. It controls the rate at which data packets are sent or received on your interface, ensuring that network doesn't get overwhelmed. By smoothing out the flow of data, traffic shaping helps prevent congestion and ensures that critical traffic gets through efficiently. So shaping is basically a QoS tool that buffers traffic that exceeds the provided committed rate. It slows down the traffic rate and sends out traffic in compliance with the provider SLA. It achieves this by queuing the messages and servicing the queue based on the shaper rate configured. You can say it buffers and delays egress traffic that momentarily peaks above the desired rate until the egress rate drops below the defined traffic rate. And if the egress traffic is below the desired rate, the traffic is sent in immediately without any delay. Let's say how the router internally processes shaping. If you look internally how the router operates, when the packet is routed out of an interface, the shaper queues the packet first, then applies round robin and priority queuing feature of CBWFQ and LLQ, and then output queuing works as normal as the traffic goes. The side effect of shaper is that it slows down the packet, which increases delay and jitter. This is due to the message simply waiting in a queue and mechanism used by the shaper, which can be reduced by configuring the shaper timings. A shaper basically sends as fast as it can and then waits, sends again waits. For instance, if we apply shaping at 200 Mbps on a router with 1 Gbps outgoing interface, in this case, the shaper would result in the interface sending data 20% of the time and then being silent 80% of the time. If you see, for 200 millisecond, it will send the traffic. Again, for 800 millisecond, it will not send the traffic. So let's take an example of a voice or video packet. Even in priority shaping queue, the packet will wait 800 milliseconds before the shaper schedules the next packet according to this time. This is too long compared to the 150 millisecond one-way delay goal for voice or video. The solution to this problem is configure a short time interval. Like for example, for 1000 milliseconds, send at 1 Gbps for 200 millisecond and then rest for 800 millisecond. Or send at 1 Gbps for 20 millisecond and rest for 80 millisecond. Or the best option I think which is recommended is send 1 Gbps for 2 millisecond and rest for 8 millisecond. So this is the recommended, the last one. I think that's it for this session. I hope this was informative for you. In my next session, I will discuss about congestion avoidance.